So when I was asked to speak here today, I just thought that maybe in the international year of the periodic table, I should just talk about this topic, the interlink between the periodic table and water treatment. And I said then a nanotechnology perspective. I would like to start by first, just advertising my university, which is too obvious. I come from the University of South Africa, and I just learned during the break, tea break just now, that many people actually are not aware that UNISA is the largest ODL learning university in the world. And actually, it's also the oldest university in South Africa. We have about 380,000 students. So you can now compare to the other universities. I studied at VETS, that's why I did my PhD. At VETS, we were at 27,000 total number of students. So UNISA actually, it's 380,000 students at the current moment. Most of these students are actually on ODL learning. Of course, we now have a number of students who are seated at the science campus where I currently sit, who are not on ODL, but who are actually full-time students who sit on the campus every day, every single day. So I'm currently based at a science campus in Florida. That's where we're situated. And I do invite those of you who don't know, quite a beautiful campus in Roodepoort, for you to come and see us. We work on nanotechnology. So my unit is called Nanotechnology and Water Sustainability Research Unit, which I lead with, we have about 60 postgraduate students, that is masters and PhD students, who are sitting in our research unit, and 10 postdoctoral fellows, as well as about 12 staff members. I invite you to just see our website when you get time. So there are quite a number of things that we are doing in the university to improve the life of people in the world. But in particular, I've already spoken about water sustainability, which is one of the issues that we are dealing with in our own unit. Before I go too further, I would like to maybe start by talking about our research focus. Briefly, I'll spend just about 3 minutes maybe talking about our research focus. What are the kind of things that we actually do in our unit? First of all, we do work on membrane science and technology, where we're just looking at various types of membrane, in particular in the issue of production and fabrication, ultrafiltration, nanofiltration, reverse osmosis, and forward osmosis type of membranes. I'm not going to bore you with so much details about the specific. I'm just going to highlight the important issues right there. We make membranes such as this one, which is typically a hollow fiber membrane that can be used as a filter. There's another area where we work on composite, bio-nanocomposites, and nanomaterials for water purification and detection. So in that case, this is a picture that just demonstrates and shows the kind of materials that we actually make using our systems and our technologies. There is also a vibrant team that works on analytical and environmental research, and I think the first speaker really spoke about some of the difficult pollutants, such as persistent organic pollutants that Dr. Mohluri mentioned in the beginning of this meeting. So there are people that are actually dwelling much on those areas, where they actually sort of like sample in different rivers and dams across the country. There's a team that also looks at the open water cycle and the rural community development, where we actually sort of like just test our technologies even in rural development. And there's a specific in rural areas, so there's a specific example which I'm going to highlight later on. And this picture just demonstrates, what you'll actually find out there sometimes. I mean, there's a whole issue that has been a buzzword for the past couple of years on the acid mine drainage, which is one of the issues that we're actually having here in South Africa. So there's also another focus that just look at bioremediation and analysis, where people are actually looking at, deploying passive samplers in water systems that stay there for maybe months, and then they actually sort of like evaluate what's the processes that happen during those times. So this was, just to give you sort of like what exactly we do as a unit based in the university. But I'm going to just highlight a few examples, because particularly for me, I'm just going to dwell much on where actually the periodic table can actually be used in some of these systems. And indeed, one of the SGDs, number 6 on clean water and sanitation, is actually what we are looking at. And let's really not forget about the issues that we're having. As a country, South Africa, we know that we're the 30th driest country in the world. And of course, that we really are a water-stressed country. As you can see from that map, that red there demonstrates that we're actually a water-stressed country. This demonstrates the importance for us to actually harness this kind of resource. I just want to then take you back once again, one step back, to just look at really, is there a link really between, the periodic table and water treatment? Of course, the answer is too obvious, and I can see the answer is actually yes. There is a link between the periodic table and water treatment. And I think the speaker that just spoke before me really did a good work in terms of like demonstrating how important the periodic table is. And we talk about critical what? Critical raw materials, yes, yeah. So that are actually found in the periodic table, and which direction really we're taking. So in our case, I'm just gonna first of all talk about what happens really in just a basic sense, what happens in the water treatment train. That picture just shows, some just steps that you will go through. And I must say that they are not exhaustive. I just pick up a few that actually go through before actually the water gets into the tap, as you can see the last stage where you step. So looking at the first one, there is primary disinfection, and then there's oxidation, which actually uses ozone, and there's oxygen that is used there. And then in the disinfection step as well as chloride dioxide, which is also one of the materials used. And the second step there is showing adsorption, and powdered activated carbon has been used for many years for that purpose. And then the third step talk about coagulation, where we are using things such as aluminum oxide and various other materials such as ions oxide as well that are used as coagulant in that process, followed by then another step called fluorination, where you actually use chlorine and fluoridation, and then it goes all the way to the final step where you actually get your water. This is just a basic statement. Countries to countries, they use different systems. Some of these you find that they swap them around. Maybe the disinfection step is in the middle or is at the end. So I've just demonstrated just now that some elements such as carbon, oxygen, chlorine, ion, various others can actually be used in the typical water treatment plant. But the issue here that we're having is that there is quite what is called a new emerging contaminant. In this case, like such as the POPs, persistent organic pollutant, that are arising, which these kind of systems are not designed to treat them in water or to remove them in water. And then that's when then we actually look at, at new technologies. What kind of technology can actually be used, to deal with this kind of pollutant. These are just, quick example. The picture is not clear here, but it's clear with me. Just to show that an example of micropollutants that are found in water systems. This So if you look below those numbers that you see there, it's just the number of countries where this type of new pollutants called micropollutants have actually been found. If you look, for example, at the last one, paracetamol is a very common drug that is used on a daily basis. It's found in about 50 countries, wastewater treatment, wastewater trains for up to 50 countries. So this is actually a serious issue that actually require attention. So that's then when we start looking at, what kind of technologies can actually be used for this kind of system. And this is the list that I already, highlighted a little bit earlier, on membranes and membrane processes, down to what is called, multifunctional devices for sensing and monitoring and detection. So here is an example which I would like to demonstrate today. The example of carbon. I'm gonna give a test, maybe asking a question after this about the electronic configuration of carbon. So you must tell me what is the electronic configuration of carbon. But this is just basic chemistry. If you go back to your high school and everything, where we're actually looking at, how each element is structured and what are the potential, bonds that you could actually form in using this particular configuration. So as I'm talking about carbon, which I said today, it's going to be my example. Carbon has got various allotropes, and we may all know that. I mean, diamond is one of them, and also graphite, which has already also been highlighted, is also an allotrope of carbon. So that's just carbon. But in this sense, where I'm looking at nanostructured kinds of carbons, that are new type of materials that have come up through the use of nanotechnologies. You call them nanocarbon, you can call them nanoscale carbon, or nanostructured carbon material is still the same. So graphene is one of them, and which, there's a picture which is supposed to show there, and it's not showing, actually, which just show you how the carbon are bonded together to give you a flat sheet in graphene. And then the second one is actually called carbon 60, which is a fullerene, also called a furylene, and it looks like just a ball, a soccer ball. So that's one of the carbons that is usually used. And then more importantly, also the carbon nanotubes is one of the important carbons that I actually use. And also I have another picture here that demonstrates, and I see it doesn't show here, it just shows how the carbons or the graphene sheets are laid together to form that carbon, and you call it a carbon nanotube. So these are the different types of carbon materials that are used and have actually, coming up nowadays to solve the problems that we are having in water systems. And once again, the flexibility of this kind of carbons is the most important thing that we're dealing with, because as a material scientist, all we're doing is just to try and play around with the properties of the material to form different types. We can have rolled kind of materials, we can have stack, you can bend them, you can top them and functionalize them. These are just the science jargon, which I don't want to actually demonstrate and show you. But in particular, I want to show you that the carbon is, that's how flexible nanocarbon is, can actually be, changed to made to be different structures. So the question will be, how is this actually made? So this is just a simple system where the carbon is actually made. So what you have just gases, in that case, such as nitrogen and acetylene, that are used in the process, and then you just need to have a substrate, and then you pass your gases through a substrate at high temperatures, and then you've got your carbon being formed there. So basically, that's a process that is used. This is actually taken from Prof Niels Colville group at Wits. So the carbons that are formed will actually have diverse diverse morphologies. I mean, as you can see there, you've got one, for example, in the middle there, that shows some like a sphere. So those are spherical kind of carbon. So it's nanocarbon, spherical kind of nanocarbon. Then you have got nanotubes, you have got vertically aligned in the middle. Then you've got spirals all the way around. So these are the typical type of carbons that you can actually have and form via this system. And once again, I'm demonstrating here that how the carbon-based adsorbents can actually be used in water treatment. There have been many examples that has been shown because of their properties, such as the high specific surface area. And they've been used in various areas, such as, you know, abstracting organic chemicals from water, as well as, you know, unwanted metal ions in water, such as lead and cadmium, zinc, etc. And then the two others, such as other nanomaterial-based examples that have also been tested. So the important issue during the production process of carbon is how they are configured on a system so that you can actually form membranes in the case of carbon nanotube membrane. So there are issues that are relating to the dispersion, and then there are issues that are relating to how aligned are the carbons, especially carbon nanotubes, how are they aligned in the polymer matrix. And indeed, the types that we have actually used are here in the board, and I'm going to just skip this slide so that I don't bore you much with the details. But also the important issue is demonstrated during the fabrication process of the membrane. In this case, you have maybe say where you start on the left-hand side, and I wish I had a pointer to show that you start with your nano tube, you mix it with an appropriate solvent, and then together down to the end where you are doing what is called phase inversion, where you get your membrane sheet to form then the membrane after the coagulation step. So basically, this is just a very simple process that is used in industry to form membranes. The phase inversion process, the most popular after hollow fiber, is the most popular one. And I hope somebody from Dow here is going to make a comment about that, because I know Dow has now ventured, is one of the people that we're looking up to, and it is probably the only company here that is able to actually make membranes and make more membrane modules. So this is just a basic process that is actually followed. It's a very simplistic process. And the important issue in our case, you need to make sure that your carbon nanotubes are actually stable on the system. So you're looking at a stable casting solution. And those pictures, they show how it will actually stand for many days in this form. Then you're able to cast it after many, many days. And then this demonstrates the type that you actually get of the membrane. So you can have a carbon membrane with those structures that you actually see in the middle, which are actually responsible for the filtration of those pollutants from water. So those structures are actually very important. So the carbon, what it does, that's sort of like control those microvoids. We call them microvoids, but literally in simple terms, is just the pore structures, how the pore is actually formed in the system. And this picture here shows different kinds, one with maybe no carbon nanotubes, and then the other one with carbon nanotubes. It actually demonstrates how the carbon nanotubes are actually responsible for controlling those voids. Those voids are very important because they're the one responsible for the filtration, for you to get a high flux in the case where you're actually filtering your water. And these numbers here are the most important. I just highlighted the most important one. You can just look at the last two, where you say pure water flux, which is very important because the pure water flux is basically how much water can you actually get after a certain period of time after filtering using this particular membrane. And then the last one here is looking at the strength, because what happens is that one of the issues is that the high pressures are used in this system. if you're using reverse osmosis, for example, uses very, very high pressures. So you need to be able to actually get a membrane with a high, with a very high mechanical strength. And in this case, if you can just look at the last column there, you're looking at 1.97, which is actually still relatively very low compared to what you are looking for. So what then happens, you just play around with the use of carbon nanotubes. And as you can see that if you look at M5 there, the highlighted M5, you have now used sort of like carbon nanotubes in that system, and you've got 4.02 megapascal, which is actually the kind of strength that you actually want for the membrane, for it not to actually break down. And it's actually comparable to what you have seen, actually, whether in literature or even in industry. And also, the last one talks about the what is called contact angle, which is just the hydrophilicity of the material. And then importantly, and one of the issues that we look at is looking at the performance then of the membrane, because you must test it in the lab before you actually go out to industry. So one of the issues that we look at in this case, if you look at the first graph on your left, it's your pure water flux. So that's your flux. So you're looking at the flux values, and you adjust the flux in our case by using the carbon nanotubes, because like I've already spoken to you that the structures are controlled by the use of these particular materials. And then on the right-hand side, you're looking at something called porosity as well, which is actually very important, because as the water goes out of the membrane, filter the unwanted stuff on the membrane, you can actually be able to look at what are the pores, how many pores, or what is the density of the pores on the surface of the membrane. Let me skip this so that I also don't bore you with much details. So in principles and in short, so we have there on your left-hand side the structure of a membrane plant. So if you go, for example, if you go to Cape Town in the desalination plant, you'll actually find you'll find the membrane configured as on the left-hand side. So that picture you see on the left-hand side. And then, but if you look in detail, actually you'll see that it's actually a spiral wound type of membrane, if you go to the right-hand side. And then finally, we can then use things such as carbon nanotubes, on that just to develop to increase or to enhance the properties of the membrane system. The testing units that we actually use during when we're testing the membranes. So basically, we are looking at, you are starting your rejection, how much pollutants are removed, and then we are testing the flux, how much water passed through. So we use this kind of a system, which is a simple cross-flow Stellitech type of a system. And as I'm nearing towards the end, so we also now have a system that we actually use to test in areas where the water is too dirty, such as the, people that are using river water or borehole water and those kind of water. We've started testing our new system that we developed. It's still, going through test, which is just a basic system that can be used, for example, in rural schools. It can be applied very well, because they're looking at water just for use by a small community of people. So, for example, those schools which are having a feeding scheme, for example, they can actually use such a technology. It's a very simple technology that uses, solar energy. So basically, the way it works is that you just have a, your mirror. So you mirror all your your rays into that mirror. Then what you have, it just hits up, the black box that side. And then what happens is then you get your whatever is inside. In this case, it's a solvent that moves across and pushes the water up through a membrane, and then you get your water just like that. So it's just a simple basic system that uses solar energy, which we have now tested. So what is happening is that now we utilize instead of using a normal membrane, we use the carbon membrane in the last step there, where we're actually doing the filtration. And then there are basic other issues, you know, on the system when you're doing the testing that you look at, such as temperature and pressure, wall temperature, various other issues that you measure. So we've got a station that looks at, that measures solar irradiation, wind speed, temperature, etc. Because remember that the weather is the most critical issue in this kind of a system. Yes, of course, and really I think I have one more slide or two slides. So we test this we test the systems in many, many schools, so just to look at, and especially in areas where there is a lot of sun. So this is just an example where we've done the test in Mpumalanga, in one of the communities there in Mpumalanga. Yes, I'm finishing up now. I hope I didn't bore you much with many details. But if there is at least something you can just take away, I think from my presentation, is that, you know, it is actually possible that the periodic table is actually still a very critical element, you know, that can actually be used in a real water treatment. And then you can actually use carbon as an example. You know, I could have used others such as boron, but I just choose to use carbon as an example. And then you form what is called carbon nanotubes, which is nanoscale carbon. That nanoscale carbon can be converted to the next one, which is just a membrane. And then the membrane can be converted to a filter. And actually the picture, it doesn't come here nicely. I've got nice pictures here. And then finally you can get clean water at the end. So I would like to actually stop here. Thank you very much for your kind